Hello and welcome to this video tutorial on interfacing of ADC0809 chip to the microcontroller 8051. ADC0809 is a successive approximation type of ADC which has the pins like V reference and minus V reference. Then there will be pin read bar, that is output enable, write bar which is start of conversion. Then ALE pin is there to latch the address. So there are 8 channels to this ADC, so there are 3 channel select lines, and when you are connecting this particular ADC to the microcontroller, this is how the interfacing looks like, where the ADC is giving the output to the microcontroller, 8-bit output, so it is a 8-bit ADC, and 8 channels are there, so these channels can be selected by 3 channel select lines A, B and C. Then there is plus V reference and minus V reference voltage. This plus V reference and minus V reference voltage connection is going to decide for what value of the analog input voltage you are going to get output as 00 to FF. So whatever digital conversion is, so that conversion depends on what is plus V reference and minus V reference. Then there is one pin called as output enable, which is a read bar pin for the ADC. So you can give the signal, see the signal directions for the interfacing. The channel selection is done by the microcontroller. The address latch enable, indicating that the channel address is available on this particular channel line, so that is a signal given by microcontroller to the ADC. Then start of conversion, so microcontroller again gives one signal, that start of conversion. These things will be clear with the help of the waveforms. Next we are going to view those waveforms. Then output enable, again signal from, so only one signal going from ADC to the microcontroller is INTR, or which is also called as end of conversion. Whenever you are interfacing this ADC to the microcontroller, the steps which you have to follow are: first you have to select the analog channel by selecting the bits A, B and C. For our simulation, we are connecting the analog input to the channel number 1, so we will select channel number 1 through channel select lines A, B, C. Then you have to activate the ALE, so it needs a low to high pulse to latch in the address. ALE low to high pulse is required, so whenever the address is available, so ALE should go from low to high. Then you have to start the conversion, so you have to activate this start of conversion. Then continuously you have to monitor for the whether the conversion is over or not. So EOC you have to monitor continuously. A high to low output indicates that the data is converted. So whenever conversion starts, EOC pin goes high, and high to low transition indicates that the data is converted into digital value and is available. So then you can give a signal which is called as output enable. Here you give the signal output enable, and whenever output enable signal is given to the SAR type of ADC, then the data, which is digital conversion of present analog input, will be available onto the data lines, and those data lines will be connected to the microcontroller. Now let us go through the code or the program to implement this interfacing. So in Keel you can write the program with the assumption you know how a Keel program can be written. So already I'm opening a project called as ADC. Let us discuss what this program is. Now this program starts with some assembler directive bit which is assigning the name to the port pins. The use of assigning names to the port pins is, if I change the pins which are getting connected to the microcontroller, means interfacing, if it is changed, still no need to make changes in the program. So presently let us say ALE is connected to P2.4. Later in some other interfacing, if I ALE pin is getting connected to P2.1, only here I need to make the change. All other program will remain same. So with this, the port pins are given some labels. So ALE stands for P2.4, SE stands for P2.3, EOC stands for P2.7, and all these are according to the interfacing which is shown here. Fine. Then after assigning the names to the port pin, you can have a program. One more thing is port 1 is assigned as a my data. Now next, org is a assembler directive you are using. Then whatever code you are writing here, whatever hexadecimal values or hex file you are getting, so that you want to load from address 000h onwards. Now what I do is I try to implement the requirement of ADC as far these waveforms are considered through my program. So whatever steps earlier we discussed, so those steps we are trying to follow. So set B EOC, so already EOC will be high, and whenever conversion is over, that pin is going to become low. So you are making EOC pin high, clear ALE, clear SC, clear OE. That is what we can say initial status. Now move my data comma hash 0FF. You know that on port 1, my data is nothing but port 1. On port 1 you are going to receive the data. The data you are going to receive onto the port 1, so port 1 has to be configured as input port. So that configuration can be done by writing FF in its corresponding latch. Now next you are selecting the address. As we have connected the analog input to the channel number 1, the analog input, this is what is the Proteus simulation file. Later I will be showing you how the program can be simulated to the Proteus. As you have connected the analog input to the channel number 1, so now in your code what you are doing is you are selecting the channel number 1. So that channel selection is done by making these three commands: set B address A, clear address B, clear address C. Now what I do is I call some delay. Now this delay is required to give some time to reach the signal and to understand what that signal is. Then what I do is I make ALE pin high. Okay, you have to send one pulse, then again I call delay, then I start the conversion. Again I call the delay and I make ALE low, means I am sending a ALE pulse so that the address will be latched. And not only that, the conversion SC I am making high, and then again I am making low. So the requirement is the start of conversion will be indicated by, means when the conversion will start, initially should be high, and high to low conversion so will indicate that the conversion will be started by the ADC. Now it will take some time for doing that conversion. So what I do is, again I'm continuously polling for the EOC. So if EOC is set, then just I'm polling, means I'm waiting that EOC should go from high to low. When EOC goes from high to low, it is the indication that the conversion is over. So when you'll come outside this loop, when EOC becomes low. Okay, so first thing is, if EOC is high, then you have to wait. The EOC will go low, indicating that the conversion is over, but EOC should be again high, low, and again high. So you want to have a pulse as far as the EOC is concerned. So you poll here, the conversion is taking place. This indicates that the conversion is over, and you wait till again you get high. So what is done is, here again if JNB EOC, still wait, and then after that what you are going to do is you are enabling the output, so that whatever the digital conversion is, that digital conversion is available to you for use. Now really how I can understand whether the conversion is correct or not. So for simulation purpose, what we are doing is whatever conversion is that is available onto the port 1, so that port 1 data I will read to the accumulator, and see just one instruction I have added for the simulation, and that instruction is the contents of accumulator you move on to the port 3, so that in the simulation what I am doing is the port 3 I am connecting to the LED bar graph, and whatever this digital conversion will be reflected on these LEDs. So this we will see while simulating this particular program. So now again I keep this program in loop so that continuously you are checking the analog input, its digital conversion will be done, the converted data will be available onto the port 1, you'll read that port 1 data and you will output it onto the port 3, and to the port 3 we will connect LEDs so that data will get reflected onto the LED bar graph. Okay, fine. Everywhere you are using delay, whenever you are sending some pulse you want to have some delay in between two values. So for that, this is small delay program. So this software delay, you write some value in some register and go on decrementing that. So these two registers are used and that value is decremented to get this particular delay. So with the assumption that you know the process to create a hex file from this particular ASM file, like just you have to build the target, the hex file will get created in the folder in which you have created the project. Prior to that, that option in the option for the target, this option should be enabled in the output. Previously it is disabled, so you have to enable this so that that hex file gets created. Now let us see, this is the program. It is written for the interfacing which is shown in this particular Proteus simulation diagram, or this is actual diagram, okay, for which we are making the interfacing between the 8051 and ADC0809. So let us try to simulate this particular code. So with this interfacing and the code, simulation is drawn in Proteus, where you have the interfacing which already I have shown. So this interfacing according to the program which is available in the Majidi book. Not only that, the same program we are using onto the RD2 kits which we have for interfacing between the microcontroller 89V51RD2 and the system. Okay, ADC cards also we have, so the same interfacing is there. So now again here what you have to do is you have to select the hex file which is the folder in which you have created this particular project. Right now I have created, I think on D drive, there is internal, can I find internal ADC of the interfacing of 8051 ADC. So this is the hex file, fine. So now I load this hex file, and then what I do is I have to run this particular simulation and see what I'm finding is, presently what I'm finding is, look at this position here. I'm finding that the input is around 5 volts. So this is 5 volt and pot is at this particular position, indicating that input is 5 volt. What I'm finding that all the LEDs are on. That is what is the conversion. So 5 volt corresponds to EFF digital value, with the assumption that your reference voltage is 5 volt and this is minus V reference is grounded. Now just what I'm doing is I will vary the analog input which is connected. So analog input, let me zoom it so that you will understand what changes I'm making. So just I'm decreasing the analog input which is connected, and accordingly the LEDs are turning off. So it is it's binary conversion. So ultimately if my analog input is 0, what I should observe? What I should observe is all LEDs are off, means conversion is 0 0. And then if I change the analog input voltage, so according to your analog input voltage, its digital conversion is done by the IC0809 successive approximation type of ADC, and your output voltage is varying from 0 0 to FF. So this is how we can make the use of ADC0809, which is of type successive approximation type of ADC, to which is interfaced with the microcontroller 8051 with the help of program. I hope you understand this particular program. The program is available in the book microcontroller programming, the microcontroller 8051 microcontroller embedded system by Majidi. The same interfacing we have considered, so this program as well as interfacing is available in that book also. The only change is there, instead of calling a function which is convert the data, what I'm doing is just converted data I'm making its output onto the port 3. Otherwise the program is same. Okay, So this is the program for ADC interfacing. Thank you.